Section 5.3 Runge Kutta methods. In this section, we'll try to solve the same initial value problem. Y prime is f of xy with an initial value. The Taylor series methods in the preceding section have the drawback of requiring the computation of derivatives of f of xy. It is tedious and quite time-consuming for most cases. That makes the Taylor methods seldom used in practice. Runge Kutta methods were developed to overcome the drawback. The methods have high-order local truncation error of the Taylor methods and eliminate the need to compute the derivatives of f of xy. The methods are formulated as in this equation. Here, W are weights such that the summation is 1, and K, J are recursive evaluation of the slope f of xy, so that this linear combination is a weighted average of the slope. Now, one requirement is here, the high-order local truncation error must be in the level of that of Taylor methods. So here we'll try to get W and evaluation points such that this combination is about Tm. Only the difference is order h to the m. This Tm is originally has such error, so that in the same level of error, we try to make that weights and evaluation points. Okay. So here we can say that Runge Kutta methods evaluate on average slope of f of xy on the interval xn to xn plus 1 in the same order of accuracy as the mth order Taylor method. Okay, here we'll do derivation case by case. First, the second order. Second order Runge Kutta method formulation is given in this way. So here yn plus 1 is yn plus h, and w1 k1 plus w2 k2. K1 is evaluated at left edge points, and K2 is evaluated at some other points. So alpha portion of the interval from xn to xn plus 1. And now y value is predicted by using the Euler method. Okay, so the requirement is that we have to decide W1, W2, the weights, and then alpha and beta, such that this weighted average is same as T sub 2 and error or the h squared. Okay, and now T2 is given in this way, and here to find the weights and alpha and beta, we try to use Taylor series expansion. Let's begin with the left hand side. That one, y sub n plus 1. That is, now once x is xn, then x plus h must be y at xn plus 1. Okay, so we have this expansion. Now y prime is f, and y double prime is same as derivative of f with respect to x, so that we can get that one. So that by using y prime is same as f, we reach at that. So here the equation can be written in this way. Okay. On the other hand, the right side of that is, here, start with this one, and we are using the K1, K2 explicitly, and then here we try to make expansion for that one, so that we try to approximate it along with the first order term, and now the error we ignore as second order, but along with this h we have third order here error. Okay, so from this one we rewrite, then now that is the same as, okay, there's y plus w1 plus w2 hf. We combine these two, and now for here h squared, we have this term and order h cubed error. Okay, that is from the left hand side. This one is from the right side, so we have to match the coefficients. Here that is the same, and here now the coefficients is 1 for h times f, so that w1 plus w2 must be 1. And also here now h squared, that is coefficients of f sub x is half, so that w2 alpha must be half. Similarly, from here we have w2 beta is half. We have 3 equations and here 4 variables, so that we may have more than one solutions, even though the number of parameters and the number of equations are the same. Because it's a nonlinear, it can have more than one solutions. For this system, we have more than one solutions. Okay, here after solving the problem, and among the solutions, these are common choices. For this system of equations, we can get here w1, w2 is half and alpha, beta is 1. Then the algorithm start with this formulation can be written in this way. So the K1 is evaluation at the beginning point of the interval, subinterval xn2, xn plus 1. Now K2 is the evaluation on the right edge point, and the function value is predicted by using the Euler method. So this algorithm is called the second order Runge method, or sometimes it is called Hume's method. Another choice is here, w1 is 0, w2 is 1, alpha, beta is half. Okay, here, before going further, look at the formulation here, and alpha and beta is mathematically must be the same, because that one is representing alpha portion of x value, and now this one is representing here beta portion of y value, but the point and the representing value at the point, if they are different, then is not really making sense. So that from the beginning, alpha and beta must be the same. In the choice here, alpha, beta are the same, so it's quite reasonable choices. Okay, when we choose these parameters, then the algorithm can be written in this form. Now, at a glance, this looks like one evaluation. Now, at the midpoint of the subinterval, and y value is predicted by using here the Euler method, and here that one evaluation. So it looks like Euler method, but it's modified. So we call it the modified Euler method. Okay. For these two algorithms, the local truncation error is order h cubed, so that the global error becomes order h squared. Okay, now let's go to fourth order Runge method. Fourth order Runge method must be formulated along with that 4 evaluations and weights. And here K1, as usual, start from left edge point evaluation. And here K2 is now by using K1, we try to predict y values and in alpha 1 portion. And here K3 is now using K1, K2 to get better approximation. Here predicted by using K1, K2, and here alpha 2 portion of the point. And K4, again, here by using K1, K2, K3, the earlier values to get here the as good as possible approximation. Okay, that's the formulation. So we have to decide the weights, alpha values, and beta values, and such that here this weighted average of the slope must be around T4. Only the difference must be here order H24. So exactly the same way as for the second order Runge method, we expand by using Taylor series techniques and then try to match here the both sides, and we have to solve the nonlinear system, and we have to choose. Here the most common choice is given in this way. That is called Runge method in fourth order. So RK4 here now yn plus 1 is same as yn plus h over 6 and 1 contribution, 2 contribution, again 2 contribution and 1 contribution, total 6 contribution divided by 6. So weights must be 1 over 6, 2 over 6, 2 over 6, and 1 over 6. Now K1 is left edge point evaluation, and K2 is midpoint evaluation using K1 predicted for y value. Now K3 is now using K2 for y value prediction at the midpoint, and K4 is evaluated at the right edge point using K3 for the prediction of y value. Okay, that's 4 evaluations here, combination. Then local truncation error must be order 5, and so that the global error is order 4. Okay, that's Runge fourth order method. For odd order, so third order and fifth order, and you can derive exactly the same way for the second order method. Idea is always the same. Okay, here we'll use RK4 to solve the initial value problem. The same problem we used in earlier. Here we define F evaluation, that is the right hand side, okay, F, and RK4, the procedure is defined here. In each level, now by saying X and W, K1 is evaluated, and now midpoint by using K1 and K2 is evaluated. Now again, one more time, at midpoint by using K2, the y value is predicted and evaluated. Now after matching here, that becomes now xn plus 1, and here at xn plus 1, the right edge points by using K3, K4 is evaluated. After evaluation, we have update, so that will be in new level, the y value approximation. So we save it. So now after running this one, we can get the y values at mesh points. Okay. Here, start with 0 and terminal point 3, and we choose 48 subintervals so that h must be 1 over 16, and y0 is 0.5, along with the ODE open and call RK4. So here we have discrete values of y. Now that is exact solution, and we try to measure the maximum error. Okay, here that is maximum error. This is a fourth order scheme. But earlier, when we are using Euler method, the first order method, we know that the maximum error is about 0.39. So fourth order method is way better than first order or second order. Okay, here we see convergence test for now RK4. We try to choose various h, the mesh size, and here maximum error is measured, and we check the ratio, here the ratio and ratio. The ideally it must be 16, but here in around the 16. Okay, so we can say that the global truncation error of RK4 is in order h to the 4. Okay, here we'll consider adaptive methods. In here, for the accuracy of numerical methods, and we may try to get better solution by decreasing the step size, so that decreasing the step size is the same as the increasing the computational cost. So that rather than decreasing step size, and here we'll try to decrease the step size whenever it is required. And so that once the solution is smoothly changing, then we may try to get larger step size. And once the solution is more oscillatory, then we can choose smaller step size. Such change of step size is a kind of adaptive methods. So here, an adaptive method is a numerical method which uses a variable step size. For example, Runge Kutta Fehlberg method, RKF45. In the method, and RK5 is used to estimate local truncation error of RK4. RK4 is main algorithm, and RK5 is used to measure the error, so that once local truncation error is large, then we try to choose the smaller step size. Once it is good enough, then very near each other, then try to choose large step size. So in this way, we can implement adaptive method. Of course, here, rather than fifth order, we may try to use a third order Runge Kutta method to estimate the local truncation error. And RK4 can be used for the main solver. And either way, you can do that. but in original setting, Runge Kutta Fehlberg method, RK5 is used for the estimation of local truncation error. Of course, you don't have to compute the RK5 solution in each level. You can do once a few in the steps. Okay, here that's the end of the section. Thank you.